Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at group problem 4b, which deals with Newton's second law and forces on an inclined plane for any type of object. I will remind you before we go ahead and start working through the problem, that copies of the problem as well as a key for the problem itself are located on Canvas. So I won't be reading through every single part of the problem, but I will be talking to you what we're going to be doing and how to go about each step of this process. So essentially our problem today is going to involve a car that is sliding down a friction plane with friction. So we will be accounting for friction on our inclined plane today, and we'll look at how to draw a free body diagram as well as how to analyze the object based on the free body diagram that we draw. So for our problem, one of the first things that we will always do is draw a picture. I'm going to combine the picture a bit with our free body diagram because they do tend to oftentimes go together, especially for an inclined plane. So here we have an object on an inclined plane today that is a car. We are given some information about the incline itself. We're told in the problem that we are looking at a hill with an angle of elevation of 30 degrees. We're also told that our car, which I'm just going to represent as a point here, even though we could go ahead and draw an entire car, I'm just going to represent it as an object. That will be our car for the sake of simplicity. We're told the car is located 25 meters up the length of the hill. 25 meters. We're also told the car's mass is 1,500 kilograms. I'm going to put that off to the side. Okay. We're also told the coefficient of kinetic friction between the car tires and the road is 0.35. We are assuming that our car's tires are locked. We're just sliding down the hill. And I believe that's all the main information that we are given. So it is important when we're dealing with any problem, especially if it's just text, to try and take that text and represent visually what's going on. That way we have an idea of really what's happening in the physical world with that problem. Now that we have that, we're going to look at the forces acting on the car itself. And before we do that, I will remind us that the question we're trying to answer is this: how fast is the car going when it reaches the bottom of the hill? I'm going to call this V1, representing the velocity at some point after we've begun to slide. We are assuming in this problem that we're beginning at rest, and we'll come back to these values later. But in order to find that velocity, one of the first things that we're going to do is look at the forces acting on the car. So I'm going to draw these forces in red so we can keep track of them and they stand out a little bit better. Since we are assuming we're on the Earth, we do have a force of gravity acting on our car that is always going to be straight down toward the Earth. We also have a normal force. Remember, we've defined this as just a force of contact between any two objects. So the car is in contact with the road. And normal force is always going to be perpendicular to the contact surface. So it's perpendicular or at a 90-degree angle to the inclined plane. Then we also have, we're told, a force of friction between the tires and the plane, or the road, if you will. And that force of friction is going to resist the motion of our object as it moves down the plane. I believe we're not told any other information about forces. So these would be our only three forces acting on the car. We have talked through over the past few weeks that when we're dealing with our inclined planes here, one thing that we will commonly do is kind of redefine our coordinate system. One thing that we have done is we have defined down the plane or just parallel with the plane as the x direction. So I'm going to refer to this direction down the plane as the positive x. We can define it as the negative x depending on what you choose, but I'm going to call it the positive x here because that's the way our car is moving. And then up off of the plane, perpendicular, we'll call the positive y. What we've talked about in class is that we're just going to reorient our coordinate system so that the motion of our object is just in one direction. So now our car is not moving partially in the x and partially in the y, it's all moving in the x direction according to this system. Now that does present a bit of a problem because now our force of gravity doesn't line up with our coordinate system, right? At least perfectly. We'll notice the force of friction is parallel to our plane, so it is in the x direction. And the normal force lines up, it's perpendicular to the plane, so it lines up with the y direction. But our force of gravity gives us a bit of a problem. And so that means we have to split our force of gravity into a component perpendicular to the plane, which we will call the y component, and a component parallel to the plane, which we'll call the x component. And the way that we have kind of shown this, or worked this out, is that we have shown that our angle of elevation is geometrically similar to the angle our force of gravity makes with the perpendicular or y component. And that's an important distinction that we need to make. So now that we have our free body diagram all drawn, as well as our force of gravity broken down into components, we want to write out Newton's second law. Because Newton's second law will help us eventually find the acceleration of our car, which will eventually lead us to finding the velocity. So primarily we're looking at the x direction here, because that's the way our car is now moving. So I'm going to start there. The sum of forces in the x direction is equal to the mass of our object multiplied by its acceleration in the x direction. Now looking at our free body diagram, in the x direction we have two forces. We have our x component of the force of gravity pulling our car down the hill, and we have the full force of kinetic friction, just so we can see that. See how those are both lined up, they're parallel with the plane. Now, the normal force, even though it does show up in the y component of our force of gravity, it does show up. Those are not in the x direction as we've defined it. So when I sum up my forces, we have a force of gravity in the x, and we have a force of friction. But that force of friction is resisting our motion, and it's in the negative x direction. So when we add these, remember we're going to add a negative value for that force of friction. If you go ahead and subtract them, that's fine too. We just want to make sure that we see they're in opposite directions, so we don't actually mathematically add them. So the sum of our forces, A, equals the mass of our object multiplied by the object's acceleration. So really this becomes a matter of, once I find my two force values, I know the mass, I can work mathematically to get to my acceleration. So how do we find those? Well, we have dealt with an equation for our force of gravity in the x direction. We've said that Fgx is just going to be our force of gravity multiplied by sine of the angle that we're given. Now remember, in case we have forgotten, the angle of elevation is geometrically the same as the angle our force of gravity makes with the perpendicular component. So x is opposite of that angle, which is why we use a sine function. So to find our x component, we simply take our force of gravity and multiply by sine theta, which is just the mass of our object, multiplied by acceleration due to gravity for the Earth, multiplied by sine of our angle theta. So here we'll go 1,500 kilograms, multiplied by g for the Earth, 9.81 meters per second squared, multiplied by sine of our angle, 30 degrees. And we'll go ahead and plug this in mathematically. Got a calculator here nice and handy. So we'll go 1,500 times 9.81 multiplied by sine of 30. Important to make sure that we're in degree mode here, not radian mode. Otherwise the angle won't be processed in your calculator the right way. So our x component of our force of gravity looks to be about 7,358 newtons. Now again, that's not the final answer we're looking for, that is just this first force of gravity in the x. So now that we have that first value, now we can see if we can find our force of friction. And thankfully for us, we have an equation for the force of friction. I'm going to work that down here. That is our force of kinetic friction is equal to the coefficient of kinetic friction multiplied by the normal or contact force between our objects. We do already know the coefficient of kinetic friction. That's given to us directly in the problem statement. The thing we don't know here is our normal force. I'm going to look back at my picture. Okay, looks like our normal force is in the positive y direction. The only other force located in the y direction is the y component of our force of gravity. Now, we're not told anything about whether the car somehow accelerates up off the plane or down into the plane. That doesn't seem to make a whole lot of physical sense based on what we've seen in the problem. So we can probably assume that those forces are equal and balanced because our car's not going to accelerate up off the plane or down into the plane. So we can probably assume that the normal force here is going to be equal in magnitude to our force of gravity in the y direction. The way that we can show that in case we're unsure how we got to that relationship is this. When we sum up our forces in the y direction, that should equal the mass of our object multiplied by acceleration in the y direction. We have the normal force directed up, perpendicular up off of the plane, plus, well, the force of gravity in the y direction, which is perpendicular down from the plane. That's a negative because it's going down rather than up as opposed to the normal force. Back in our picture, normal force perpendicular up from the plane, y component of gravity perpendicular down from the plane. And if we're assuming we're not accelerating in that direction, our acceleration would be 0. Whatever the mass is times 0, doesn't really matter what our mass is, that's going to give us a value of 0. Then I can add over my force of gravity in the y to show that the normal force is equal to our force of gravity in the y, which again is really just a way of us mathematically showing why those forces are equal. It is important that we understand the fact that they're equal, but more so we know why they're equal. It's not just the fact that they're equal, we need to know why. So our normal force equals our y component of our force of gravity. We have an equation for that. That's just going to be our force of gravity multiplied by cosine of our angle, because that component, the y component, is adjacent to the angle we have. So to find our y component, we just take our mass of our object multiplied by g for the Earth times cosine of our angle theta. So mg cosine theta. So we've got 1,500 kilograms times 9.81 meters per second squared multiplied by cosine of 30 degrees. So we'll plug our values in. 1,500, 9.81, cosine of 30. So we get about 12,744. Now remember, this is not the actual force of friction. This is just the normal force, which will help us get to the force of friction. So now we're going to plug back into this equation here. So I'll bring that down and rewrite it. F sub k is equal to mu sub k, our coefficient of kinetic friction, multiplied by the normal force. We know the coefficient that was given to us at the beginning of the problem, 0.35. Now we have our normal force, 12,744 newtons. So we'll take the value that we just had. If you left it in your calculator, that's nice and convenient. We can just multiply that value by 0.35. We get approximately 4,460 newtons. That zero is going to bother me. There we go. Get that up a little bit. So now we have our second force that will show up in Newton's second law in the x direction. So we've got F sub k. We also have F sub g in the x. So now we're going to come all the way back up to the very first equation we wrote down, Newton's second law in the x direction. Because we want to get our acceleration so that we can find a velocity. So I'm going to rewrite this equation on a new page. This one's getting a little bit bulky. Actually, I could just extend it down. That works too. So now we'll come back here. We had a sum of forces in the x direction equals the mass of our object multiplied by its acceleration. So we have F sub g in the x minus F sub k. Remember, we're just plus a negative, so we can write that effectively as just subtracted by. Is equal to mass times acceleration. So now we'll plug in what we know. Our force of gravity in the x was, let's see, 7358 newtons. Minus 4,460 newtons. That equals our mass, which we actually know, so I'll go ahead and write that in here. 1,500 kilograms multiplied by the acceleration in the x direction. So we know our two values on the left-hand side of our equation. I'll go ahead and subtract those. 7358 minus 4460. So I get about 2,898 newtons is equal to 1,500 kilograms multiplied by acceleration in the x direction. And then to get acceleration in the x by itself, I need to get rid of this mass. So remember, because our right side of Newton's second law is mass multiplied by acceleration, we have to divide by mass to get acceleration by itself. I can't just subtract that value. I have to divide it out because it's connected via multiplication. So we'll take 2898, divide by 1500. We get a value for our acceleration in the x direction of approximately 1.93 meters per second squared. So this gives us our value for acceleration, which, again, I know it seems like a lot, is actually not the final answer we're looking at, but now we're very close to getting to our final answer. Before we move on, because once we have this value, it's really just a matter of using a kinematic equation. Before we move on, I want us to understand the process that we went through. So remember, the skills for analyzing an object on an inclined plane are really no different than analyzing an object on flat ground. We still drew a picture, we still drew a free body diagram based on that picture, and then we applied Newton's second law. We're not doing anything noticeably different. The only thing that changes is we slightly adjust our coordinate system to account for our object being on an incline rather than being on flat ground. But we're still going through the same process that we've always gone through. Picture, free body diagram, Newton's second law, and then we start to work through any equations that we have that can help us solve Newton's second law for the value that we're looking for, which here is the acceleration. So now, to bring all of this together, this becomes really a kinematics problem. We know we're traveling a displacement of 25 meters in the x direction down the plane. We're told we are starting from rest, so our initial velocity is 0. We want to find our final velocity here, so put a star by v1. We just solve for acceleration in the x direction, 1.93 meters per second squared. And time is our one variable that we do not know and that we're not really concerned with here. We could solve for it if we wanted to, but the question's really about how fast we're going, not how long it takes us to get down the plane. So we don't need time, which tells us, I believe we're going to use equation number 5, which looks like this. V1 squared is equal to V0 squared plus 2a delta x. Now before we plug in any values to that equation, I already know that V0 is going to be 0. We're starting from rest. And 0 squared is still going to be 0. So I can actually simplify this equation down in this setting to be V1 squared is equal to 2a delta x. And then you'll notice, even before I plug in any values, to get V1 by itself, all I have to do is take a square root, and this way I can come up with my equation before I deal with any numbers. And then I can just plug in all the numbers at once. So if I take a square root of both sides of my equation, the square root of V1 squared is just going to be V1 is equal to the square root of 2a delta x. So now I have an equation that I can use to solve for V1 directly. So V1 is equal to the square root of 2 multiplied by 1.93 meters per second squared multiplied by delta x, 25 meters. So now we have 2 times 1.93 times 25, take a square root, we get a value of approximately 9.83 meters per second. Now, one thing that's important, when we take a square root, we actually get two answers, positive or negative, 9.83 meters per second. But look back at our problem statement. We defined a going down the plane as the positive x direction, which means our object, according to the x direction, this is v1 in the x, should actually have a value of positive 9.83 meters per second because it's moving in the direction that we've defined as positive. Remember, we get to control how we define positives and negatives, as long as we're explicit and clear with the choices that we make. So this is a great example of a full scenario involving a free body diagram, applications of Newton's second law, and then taking those values to solve something like a kinematic equation to find a velocity. So hopefully this gets us the right direction for looking at group problem 4B. If you do have questions, don't hesitate to ask. And remember, there is an extra copy of your key located on Canvas. Best of luck.